Good afternoon. I would like to introduce Fedotov from the University of Petersburg, and we talk on Maryland equation, renormalization formulas, and minimal meromorphic solutions.
Thank you very much. And as traditional, I would like to thank the organizers for having me here and giving me the opportunity to give the talk. Thank you very much. This work was done in collaboration with Fedor Sandomirsky, one of my students from St. Petersburg State University. Actually, Maryland equation was written already by Svetlana Zhitomirskaya, so I begin my introduction by another object, by describing another object closely. I want to recall some results because they are closely related to the Maryland equation, to the topic of today's talk. I'm going to speak about Gaussian exponential sums first at the beginning, which are well known in number theory. So the nth sum is just the sum containing n exponentials, and the nth term is just the exponential of a second order polynomial of n, or the index of summation. Here in this formula you have two constants, omega and theta. Omega is supposed to be a number between 0 and 1, and theta is between minus 1/2 and 1/2. Well, being related to the analytic number theory, this object was studied by many authors. I cannot write the full list of names, it's very long, but among the people who had studied this object is Cauchy, Gauss, Hardy, Kronecker, Littlewood, and so on. Jens Markloff, who is also visiting this term. For the first time, I heard about this equation during a talk of Michel Mendès-France, made in France. And he had produced a lot of beautiful pictures similar to this one. And what is on this picture? On this picture we plot, so this picture is on the complex plane. And on this picture we plot consequently the values of the consequent exponential sums. First for n equal to big N equal to 1, then for large N equal to 2, and so on. So there are about several thousand points. So roughly you see a continuous curve, which has a rather sophisticated structure. Actually, if you take a microscope, or I don't know, probably in this case you have to take some magnifying device, you'll see that the curve consists of small spirals that form larger spirals, this one, that form a larger spiral. It begins somewhere here, and the color changes with n. First the color is red, then it's yellow, then it's green, then it's blue. Okay, Mendès-France has explained these pictures by means of an approximate renormalization formula, which roughly relates a sum with n terms with a sum with a smaller number of terms. And he told me that because of this relation, you, when studying a sum with a large number of terms, you see a lot of graphs of sums with smaller number of terms. But when I was trying to ask him about analytical details of the proof of this phenomena, he could, to my great surprise, he could not provide any details. And yeah, you have points. S of 1, and big N is equal to 1, S of 2, and so on. No, these are not dots. These are small, very small spirals. They are very small because here you have several thousand points. But small spirals form larger spirals, and larger spirals form again larger, this spiral one, and you can continue this, and you'll see the similar multi-scale structure. And that is why, because Mendes France could not answer my question, me and my co-author, one of the organizers of the term, Frederick Klopp, we decided to understand it ourselves, and we have written the following formula, renormalization formula. Here in this formula you have the input Gaussian sum, and here another Gaussian sum with new parameters, frequency omega 1 and ergodic parameter theta 1 instead of the frequency omega and theta. And omega 1 is related to omega by means of the Gauss transform. N1 is related to n by means of this formula, where these brackets stay for the integer part. And as omega is smaller than 1, you see then that n1 is smaller than n, and the new sum contain less terms there than the input sum. And actually, what is the novel? Many people have written renormalization of formulas. What is the novel here? Because usually people write only the first line and plus estimate of the term that they have called an error term. And we have obtained an explicit expression for this term, which actually is not an error term, which is important. Yeah, it's a closed, sorry, it's a closed formula. It's a closed formula. I copied this formula here on this blackboard. You just express one exponential sum in terms. Oh, I have forgotten here the main, the most important term. I have forgotten here the exponential sum, s conjugated of n1 omega 1 theta 1 plus. So you multiply this exponent by the sum, and then you have an additional term, simple exponent multiplied by this special function. Okay, what is this special function? This special function is described by this simple contour integral. In the numerator you have a quadratic exponential. In the denominator you have the simplest periodic function, periodic with the period 1. It has zeros at the points psi equal pi equal to xi plus 1, minus 1, and so on. There is a series of zeros of the denominator, and the contour path as shown in the figure. Roughly it goes from minus I infinity to plus I infinity, and roughly across xi, but more precisely along an infinitesimally small half circle go around of this point. We were very glad when we have introduced this function, but later, unfortunately, we have discovered that similar function appeared already in works of other mathematicians, unfortunately. Okay, what are the most important properties? Well, there is a long list of important properties of this function, but the first, the main for us are here. The first property. Sorry, in Russian. So the first property is this first order difference equation. F capital as a function of xi satisfies to this first order difference equation on the complex plane of xi. Second property, well, I would like first discuss the third one. Third property is that it satisfies simultaneously one more difference equation, independent of the first one, because here you have a different shift parameter. Here the shift parameter is equal to 1, and here it is equal to omega. And actually there is, so it's very characteristic, the fact that this special function satisfies simultaneously to two different difference equations. And actually there is a bridge from the first equation to the second equation, which is independent of the integral representation I have written. In fact, this function I have described by the integral can be uniquely characterized as the minimal entire solution of this equation. It's an entire solution with the slowest possible growth as imaginary path to xi tends to plus or to minus infinity. Minimal possible growth. Okay, and the last property, which is very extremely important for describing the geometry of the picture we have seen, is this asymptotics. So if omega is small, then you can estimate roughly our contour integral roughly by the saddle point method, and you'll see that f calligraphic, f capital has this asymptotic expansion, and the leading term is just expressed in terms of the Fresnel integral. And actually, on the picture that we have seen before, I repeat it once more for your convenience, you see a lot of graphs of Fresnel integral. This is a piece of the graph of the Fresnel integral. This again Fresnel integral, and this small objects that somebody has called dots are also small graphs of the Fresnel integral. And the
connected sort of. It's all one connected sort of. It's not. It's really connected. It looks a little bit as if it would be disconnected.
no, it's connected. It's connected, but it contains a lot of points, and there are three types of spirals. These very small ones, they are not dots, they are spirals. Then you have these spirals, and then you have a big spiral, a large spiral. Okay, and actually, the first, the tiny spiral that you cannot see, but you consider it as a dot, can be obtained immediately after the use of this renormalization formula. Actually, if n is such, if n is smaller or is smaller than r over 1 over omega, then n1 equals to 0. And your input exponential sum is just the sum of two of this combination is just this combination of the special functions f. And this combination is roughly described by Fresnel integral, and you see the smaller spiral, very small one. To describe the behavior of this exponential sum with larger number of terms, you have just to apply this renormalization formula once more to the sum which is in the middle. Then you get, then you see that if n2, which is equal to integer part of omega 1, n1, which is equal to omega 1 integer part omega n, if n2 is 0, then actually your sum is described by two combinations, as a sum of two combinations of the functions f. The first combination of the functions f gives you small spiral, and the second combination gives you this spiral. And the whole picture can be explained after three renormalizations. But I am a little bit cheating. I shall explain you where I am cheating. Omega is a rational number between 0 and 1. So it can be represented by an infinite continuous fraction with positive integer elements n1, n2, n3, and so on. So if you plug this formula into the definition of omega 1, you get this representation for omega 1.
So omega is irrational. So you have
irrational, well, for simplicity, yeah. It's the most interesting case. And roughly you see that what is the difference between omega and omega 1? It's just one floor of the continuous fraction. You just erase the first floor of the continuous fraction for omega, and you get the continuous fraction for omega 1. And this implies the following thing. This implies that if all the n1, n2, n3, and so on are large, sufficiently large, then all the omegas that you get in course of the renormalizations are small. So in all the renormalization formulas, you can replace the functions f by the asymptotics containing the Fresnel integrals. And then you arrive to this figure, to this picture. So you get the most beautiful picture if all the n's are sufficiently large. If they are not very large, you get also beautiful pictures, but not as beautiful as this one. Okay. And now I can come to the Maryland equation. Actually, Svetlana Zhitomirskaya has already written this equation, but I made a very little change. I replaced here tangent by cotangent. It will be more convenient for me, but in fact it's the same equation. Now it's a different equation on the integer lattice. There's a difference equation on the integer lattice. The different Schrödinger equation, because you have the sum of psi chi plus 1 and psi chi k minus 1 is discrete Laplacian. Here you have a potential. You call, because of this, you call lambda a coupling constant. Lambda is larger, is positive. And omega, you have also parameters omega and theta. Omega, as in the case of the exponential sums, is called frequency, and theta, as in the case of exponential sums, is called ergodic parameter, the ergodic parameter. And as we are participating in a conference on the spectral theory, you recognize easily here the spectral parameter E. Okay. In this equation, there are two natural frequencies. The first one is related with to the period of cotangent. So there is one period equal to pi, and the second is the distance between two consequent arguments of the function cotangents in this formula. It's equal to pi omega. Because of this, it's natural to consider this equation as two frequency quasi-periodic equation. It becomes quasi-periodic when omega is irrational, when the periods are incommensurate. This equation, as Svetlana told, has appeared in solid-state physics. It was invented by Fishman, Grempel, French as a non-trivial quasi-periodic equation, which can be studied more or less efficiently. And it was studied by many mathematicians, for example, Fegotin, Pastur, Simon, many others, and Zhitomirskaya, who made a talk, gave a talk a few days ago on this subject. Okay, Zhitomirskaya has described in detail all the spectral properties of this equation. I mean all the properties of the spectrum. When the spectrum is singular continuous, when the spectrum is pure point, and so on. But our ultimate aim is to describe the details of the behavior of solutions of this equation for large values of k, large coordinate asymptotics of solutions. And actually, physicists have made a lot of calculations. And here, on this figure, we have a result of one of the results of such computer computations. Here, along the horizontal axis, we plot the integers, and along the vertical axis, we plot the absolute values of the eigenfunctions and eigenfunction of the Maryland equation. So at first point, somewhere here we have, or probably here, we have absolute value of psi of 1, then absolute value of psi of 2, then absolute value of psi of 3, and so on. And this points are again interpolated by straight lines, and we see roughly a continuous curve with quite a complicated structure.
So this is a typical eigenfunction?
It's a typical picture, And what do we see here? We see essentially the same pattern, which repeats many times. But if you take a microscope and look at a piece of this picture under the microscope, you'll see the same structures. It roughly recalls what we have seen in the case of exponential sums. And well, the physicists speak about multi-scale, multi-fractal behavior. And of course, there is a beautiful problem to explain this behavior. And actually, I will describe a renormalization formula, which is very close to the renormalization formula from the theory of Gaussian exponential sums. Sums have almost the same structure, but not. Here you have additive structure, and for Maryland equation you'll obtain. We have a renormalization formula of multiplicative structure, and I shall describe it in a few minutes. Everybody of us knows that any any reasonable second order differential equation can be written equivalently as a system of two first order differential equations. Of course, you have the same thing for difference equations, and Maryland equation is a second order difference equation, and it can be written as a system of two first order difference equations, or equivalently in this matrix, or if you like vector or matrix form. Here M is 2 by 2 matrix described by this formula. You have here spectral parameter minus lambda times cotangent, and this equation is equivalent to the Maryland equation, first order equation equivalent to our first order matrix equation equivalent to the second order difference equation, Maryland equation. Okay, now suppose that you know p at the point 0 for this equation. Then just by using this equation you can easily compute p of 1 at the point 1, right? At the point 2, 3, 4, and so on. And moreover, as the matrix M is obviously invertible, you can compute p at the point -1, -2, -3, and so on. So it's just to know the solution. A solution you have to know it at the point 0. Okay. We can see the solution satisfying this initial condition: p of 0 equals to identity matrix, and we call this solution a fundamental matrix solution of the matrix Maryland equation. We'll call this equation matrix Maryland equation. There will be 3 Maryland equations, and this is the matrix Maryland equation. The fundamental solution actually can be computed more or less explicitly in terms of the matrix M. If, for example, if k is positive, then p of k equals to m of theta times m of theta plus omega, and so on, times m of theta plus k minus 1 multiplied by omega. Similarly, you can compute p of k for negative k. Okay. If you use a terminology from the dynamical system theory, you can speak about cocycles, matrix cocycles, generated by this matrix function, and rotations on the unit circle. But I don't want really come into the details. And now I'm going to describe the main result in renormalization formula relating p of k in terms of it's the product is the fundamental solution of the matrix Maryland equation. It's the product of this ergodic product of such matrices. And I am going to express this ergodic product in terms of of a similar ergodic product with a smaller number of terms, as for exponential sums.
Would you minus the
Where?
last line, the first factor?
Minus, 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 right. Thank you. I cannot change now. I cannot. Thank you very much. Okay, and the formula is following. Sorry, to write the formula I have to introduce some new parameters, because the formula, final formula become the most interesting if you introduce these new parameters. So in the input equation you have the spectral parameter E and the coupling constant lambda. And now instead of this spectral parameter E and the coupling constant lambda, I introduce two new real parameters, eta and L. I suppose that L is positive and eta is between minus pi and pi. Under this condition, this equation with real E and lambda defines eta and L in a unique matter. Actually, this is a simple exercise. You can compute explicitly lambda and E in terms of L and eta, and also you can compute explicitly eta and L in terms of E and lambda. I dropped the second expression for L and eta in terms of E and lambda. But I want to notice one important detail. We shall return to this detail later several times, that if lambda is large, then as seen from this formula, L must be large also. L is roughly of order of log lambda. So if either lambda or L is large, then roughly one is of order of logarithm of the other. And now we are going to use these two parameters, so instead of E and lambda, and so we adjust our notations. Now we have m of z of eta L and p of k omega theta eta and L. And that is the main result, the renormalization formula. It can be used to describe the multi-scale structure of solutions, but let me speak first about this formula. So here you have a matrix fundamental solution for the input matrix Maryland equation with the parameters omega, theta, eta, and L. Roughly, it's an ergodic product of large M matrices. Yes, right? I have written it here also for your convenience. P of k is the product of k matrices, ergodic product of k matrices. And here you have again a fundamental solution, the fundamental solution of another matrix Maryland equation, as in the case of exponential sums. But with the new parameters, omega 1 instead of omega, theta 1 instead of theta, eta 1 instead of eta, and L1 instead of L. The relation between old frequency and new frequency is exactly the same as in the case of exponential sums, the Gauss transform. The number of factors in the product Pn1 are related similarly to the case of exponential sums. Here you have n1 equals to integer part of the product omega times n, and here you have n1 up to the sign equals to integer part of roughly n omega. And this again is if omega is as omega is between 0 and 1 and n is sufficiently large, obviously n1 is smaller than n. So at least if n is large, you using this formula, you can diminish the number of terms in the matrix, ergodic matrix product PM. You get ergodic matrix products with smaller number of terms. Okay. So there are also some well, correction terms, which are not correction terms, important terms, but I have written here them. Matrix, they are expressed in terms of one special matrix function, capital F. And I shall speak a lot about this matrix function, but I just want to compare one formula to the other. Again, you have here exponential sum, input exponential sum, new exponential sum, and two correction terms. The formula is additive, and here you have old matrix product, new matrix product, and some correction factors. The most interesting thing is the description of these two matrix factors, f and f to the power -1. This matrix function actually can be can be described in terms of only one, scalar function, small psi. And this small psi is a solution of the equation that we call a complex Maryland equation. So this is the third Maryland equation we work with. In the input Maryland equation, matrix Maryland equation, and this complex Maryland equation. Small psi is a solution of this Maryland equation, complex Maryland equation. An equation that you have to consider on the complex plane, and you search solutions of this equation as function defined on the complex plane. Here your shift parameter is equals to omega, and one of the coefficients of this equation is meromorphic. So it's very natural to discuss meromorphic solutions of this equation, and this function small psi can be characterized as a minimal meromorphic solution to this equation. What does it mean, minimal meromorphic solution? I shall explain it in detail, but roughly it's a solution with the slowest possible growth when imaginary part of z, tends to plus infinity and to minus infinity.
There is only one.
Up to a constant.
Is omega real or omega is
real? Real. Omega is real. Up to a constant factor. It's unique up to a constant factor. Okay, and now I have to describe, to complete the description of the result, I have to describe what is this minimal meromorphic solution. Actually, the idea of minimal solutions was introduced by Buslaev, Vladimir Sailich Buslaev, my teacher, and me, when we were studying difference equations with entire coefficients on the complex plane. And we have introduced idea of notion of minimal entire solutions. But I shall speak about it a bit later. Let us come to the Maryland equation, complex Maryland equation. Look at this equation. You have here psi of z plus omega, psi of z minus omega, and psi of z. And only psi at these 3 points. And that is why actually this equation is invariant with respect to multiplication by this exponential, the simplest omega periodic exponential. Of course, is invariant with respect to multiplication by any omega periodic function. If you have a solution, you multiply it by this exponential, you have again a solution. If you have a solution, you multiply it by any combination of powers of this exponential, you get again a solution. This observation immediately leads to the following conclusion. Suppose that you have constructed a meromorphic solution of this complex Maryland equation, just one. But then you can multiply it by any trigonometric polynomial periodic with period omega. But this implies that there are meromorphic solutions growing as quickly as wanted, as imaginary part of z tends to plus or minus infinity. You multiply by cosine, you obtain already a solution which grows quicker as at plus I infinity, so at minus I infinity. This observation leads immediately to the question if one can construct a minimal meromorphic solution. We believe that all the solutions are meromorphic, as the coefficient cotangent is meromorphic. If you can construct a minimal meromorphic solution.
And can one produce every solution of the minimal by this linear combination of translates and so?
Wait a minute. To describe a minimal meromorphic solution, we have actually imposed a condition on the set of poles of this solution. Because otherwise you can divide. You can take a meromorphic solution of this equation and divide this meromorphic solution, say by cosine, omega periodic cosine. Then you add poles, but your solution will increase slowly at plus and minus I infinity. So first you have to make some additional assumptions on the set of poles. And we call the minimal meromorphic solution, the solution that has no poles in this strip and has the slowest possible growth as the imaginary part of z tends to plus minus infinity. Of course, if you take another similar strip, you get another meromorphic solution, but probably it will be more quickly increasing. It depends on the choice of this strip free of poles. Okay, so
The rate of growth might be different as plus minus close to infinity.
Imaginary, it has the slowest possible growth simultaneously as imaginary part tends to plus infinity and as imaginary part tends to minus infinity. You have to control the rate of growth simultaneously at both the infinities. Otherwise, just by multiplying by this exponent, you can.
Then could you switch?
You can switch. I shall probably discuss, but I don't believe in it, the definition of the minimal meromorphic solution in more details, but I just, for a moment, I just claim that it exists, and then there is a beautiful observation. It appears that if it satisfies the complex Maryland equation, if we have a minimal meromorphic solution satisfying the first Maryland equation, it satisfies also one more difference equation, independent on the first one, because here you have the shift parameter equal to omega, and here you have the shift parameter equal to 1. This recalls the characteristic property of the function f, which was also satisfying to two different difference equations at the same time, simultaneously. And you replace here omega by 1, lambda by lambda 1, e by e1. Just few comments. What do we do to compute lambda 1 and e1 in terms of e and lambda? First, in terms of e and lambda, we compute the parameters L and eta. You remember I have introduced these two new parameters. Then, by these formulas, we compute L1 and eta1, and then we recover lambda 1 and e1. And that is the second. And this observation is one of the two key observations leading to the renormalization formula I have written. Because the formula for the minimal meromorphic, Svetlana Zhytomyrskyaya told that actually Maryland equation is somewhat exactly solvable. From the point of view of complex analysis, it means that you can explicitly construct some solutions of this equation. And actually, the minimal meromorphic solution also can be constructed by an explicit formula. I shall discuss.
Last question. What do you actually mean by smallest possible?
I tried to explain it. I haven't succeeded.
Okay.
You consider the absolute value of your solution.
Yeah.
And as I have told, if you have just one solution, meromorphic, then because of the invariance of the input equation with respect to multiplication by omega periodic functions, you can multiply your solution by omega periodic trigonometric polynomials, for example, and then you can get solutions which increase quickly, more quickly.
Yeah, this is I understand, but what does it mean the smallest possible? Does it mean that if you take any other solution,
It increases quicker.
What does it mean? It increase uniformly?
I can describe, if you permit me, I answer this question after the end of the talk.
Okay,
You just repeat the question. Our chief will command to ask the questions. You ask your question and I answer with my pleasure. Like this, I will arrive to finish my talk before 4. Okay, and the minimal meromorphic solution also can be constructed by an explicit formula in terms of a beautiful special function which I call sigma. And this beautiful sigma satisfies to the first order difference equation on the complex plane equation of this form. Actually, it recalls very much gamma function, Euler gamma function, because Euler gamma function, what is the equation for the Euler gamma function? You have gamma of z plus 1 times the simplest first order polynomial times gamma of z. And here you have sigma of z plus h equals to the simplest first order trigonometric polynomial times sigma of z minus h. And this function has a long list of beautiful properties comparable avec the list of beautiful properties of the Euler gamma function. One of the properties is that it, if you consider a minimal meromorphic solution to this equation, then you find out that it satisfies immediately one more difference equation independent of the first one, because you have differential parameters. This beautiful function first was found by specialists in diffraction theory, Maluzhinets, Russian mathematician working on diffraction theory. He was studying scattering of waves on the angles. You have a plane wave, it goes to an angle, there is a scattering, diffraction, and when describing the scattering and diffraction, he found this function. Then this function was rediscovered in the theory of integrable systems by Ludwig Fadeev and Sasha Volkov. It was rediscovered independently in the theory of quasi-periodic equation by Buslaev and me. And finally, it was rediscovered independently in the theory of special functions. And each author was extremely glad. And okay, so and the fact that sigma satisfies simultaneously to these two independent difference equations also implies independently that the minimal entire solution psi satisfies to two different Maryland equations. Okay. So I told that the way to the renormalization formula that I have described is based on two different ideas. The first idea was the idea of the minimal entire solution, and the second idea is the monodromization idea. Let me say a few words about the monodromization idea. The monodromization method was proposed first by Buslaev and Fedotov when trying to repeat famous results of Bernard Elfer and Johannes Sjöstrand, and first results on constructive results, results describing constructively, in constructive manner, the geometry of the spectrum of the Almost-Mathieu equation in semi-classical, in some sense in semi-classical limit, and then trying to repeat their work we arrive to this monodomization idea. And let me explain very briefly what is this this idea. So consider this finite difference equation on the complex plane. So in this equation you have a 2 by 2 matrix M of z. And the determinant of this matrix is 1. It's a unimodal matrix. Suppose additionally that M is 1 periodic. Okay, then all our input equation is obviously invariant with respect to the translation by 1. And so you can try to proceed as in the case of differential equations and define a monodromy matrix. So you take psi of z plus 1, it satisfies to this equation together with psi, simultaneously with psi, invariant, equation is invariant with respect to the translation. And you can express psi of z plus 1, one more matrix equation, solution, in terms of the fundamental solution. Fundamental solution, of course, you have to suppose that psi is a fundamental solution. In this theory, fundamental solution, matrix fundamental solution is a solution with unit determinant. So you can express psi of z plus 1 in terms of psi of z, which is a fundamental solution.
Is it T to transpose M and T, M and T?
I shall explain. If it were a differential equation, first order differential equation, then here you would put a constant matrix. Monodromy matrices for periodic differential equations are constant. For difference equation, you have to put here an H periodic function. And here I have written T is just transposition for sake of convenience. And I have written in the argument H, Z for M to be 1 periodic. So in the definition you have right here an H periodic matrix. And I have written such a strange expression to get a 1 periodic matrix M1. We call this matrix monodromy matrix. M1 we call monodromy matrix. It's just direct generalization of the idea of the monodromy matrix for differential equations. And it can be easily seen that this matrix share properties similar to the property of the main properties of the matrix of the input equation. It's 1 periodic, and the determinant of this matrix is equal to 1. Okay, now trying to proceed as in the case of differential equation, we have arrived to one more difference equation defined by the monodromy matrix. So here you have the monodromy matrix, and here you have a new shift parameter. The new shift parameter is related to the old one by means of the Gauss transform. And what is the relation? There are many deep relations between these two equations. In particular, one can show, and this is not completely trivial, that in terms of any the behavior of solutions of the input equations mimics or copies, roughly speaking, the behavior of solutions of this equation at infinity. This is the crucial point. And having constructed a solution of the monodromy equation, you can construct a solution of the input equation. That is what was done when writing our renormalization formula. We express a solution of the input equation in terms of solutions of the monodromy equation, actually. Again, now, you can ask the question, when this passage from the first equation to the second equation is efficient? Of course, the answer, well, the first condition which comes to you immediately is you want for the matrix M1 to be as simple as possible. With Buslaev, we have considered matrices that were trigonometric polynomials. And our main question was if one can construct a fundamental solution such that the corresponding monodromy matrix be also a trigonometric polynomial of the same order. And it appeared that for the monodromy matrix to be the simplest possible, you have to take the solution of the input equation, the entire solution of the input equation with the simplest possible behavior at infinity, plus minus I infinity. It is the minimal entire solution. And this relation between these two equations, input equation and monodromy equation, for the in the case of Maryland equation, plus the choice of psi as a minimal meromorphic solution, in this case, has led to our renormalization formula. We get renormalization formula using this monodromization idea and the idea of the minimal entire meromorphic solution.
But M1P is the transpose of M1?
Transpose, yeah. I told transposition, yeah. Okay. And well, I have to finish quite soon, and I just mentioned one of our results with Buslaev. Consider this three parameter matrix family. You have S, T, lambda, constants. A is also constant. A constant is expressed in terms of S and T in such a way that the determinant of M be equal to 1, actually. This is equivalent to this formula. So in some sense, it's the simplest first order trigonometric polynomial with the determinant equal to 1. Matrix polynomial with the determinant equal to 1. This matrix family, well, we can now consider the corresponding difference equation psi of z plus h equals to m of z times psi of z, the corresponding difference equation. And it appears that if you choose in this family s equal to -1 and t equal to 0, you arrive to the equation which is equivalent to the complex almost material equation. You remember we replaced the Maryland equation defined initially on the integer lattice by the complex Maryland equation. And this complex almost material equation is related in the same way with the usual Maryland equation. So roughly speaking, between among the equations with M from this family, you can find also the almost material equation. And one of the results that was obtained by Buslaev and me was the following: there exists a minimal entire solution to the equation with this to this equation with this matrix, such that the corresponding monodromy matrix has of this form. What is the difference? You have just replaced S by S1, T by T1, and lambda by lambda1. The relation between lambda and lambda1 is very simple. And actually, as we understand now, this theorem reduces the analysis of the solution, say, of the almost material equation at infinity to the analysis of the dynamical system that computes S1 and T1 in terms of S and T. Well, here I am going to stop. Thank you very much for your attention.
Questions?
There is one.
That's my question.
Okay.
So, what is the exact definition of a minimal solution?
Okay, I can do it. But if I can do it, I would like to. Is it possible? Is here some button?
Will you erase this one, no?
Yeah, I shall erase this one.
Okay.
Fine. Great. It's a miracle. It's a miracle. So you have, let me explain this in the case of the Maryland equation, okay? You have psi of z plus h plus psi of z minus h plus lambda cotangent of pi z psi of z equal to e psi of z. First, let us assume that we work in a neighborhood of plus I infinity. That is, the imaginary part of z is sufficiently large. Then heuristically, you can replace cotangent by its asymptotic. So you get roughly the following equation: plus psi of z minus h plus let me check. If we go up, we get minus 2i psi of z equal to e psi of z. Lambda, okay, lambda. This is the second order difference equation with constant coefficients. And one can easily construct two solutions of this equation of the form e to the, well, there is some combination of e and lambda, I think, of eta and del. You remember I have,
Yeah, that might.
well, some phase of which depend of eta and del. Times z plus small o of the o1 as imaginary part. Oh, sorry, for this heuristic equation you have equality. And then you can prove that this equation also has solutions of this form, but of course with some small correction. As imaginary part to z tends to plus infinity. Huh?
Check, I follow the red null factor too, right?
Huh?
Minus I, but not minus 2i, right?
Minus I don't know why I have replaced lambda by 2.
Lambda was not.
It was lambda. Actually, it was lambda. You haven't understood. Okay. Now, our solution actually has poles. The minimal meromorphic solutions. It can be easily seen that it has poles only on the real line of that. And so it's analytic in the neighborhood of plus infinity, infinity. Here in this neighborhood, the solutions plus and psi plus and psi minus form a base in the space of solutions. So you can write psi of z equal to a linear combination of these two functions. And if you work psi minus, and as you work with a difference equation, the set of solutions is larger than in the case of differential equations. Here you have to add some h periodic functions. A b of z plus h equals to a b of z. So you can do so. It's above, near to the point in point plus I infinity. You can do the same for the point for a neighborhood of the point minus I infinity. Minus I infinity plus d do z psi minus I infinity of z. Here you have C and D, also some periodic function. It just follows from the fact that psi is meromorphic. It has zeros only on the real line, and that is all. Now, the rate, these solutions, psi plus and psi minus, are fixed. The rate of growth is fixed. And so, obviously, the rate of growth of psi at plus I infinity is determined by the rate of growth of these two periodic functions. Similarly, the rate of growth of psi of z at minus I infinity is determined by the rate of growth of these two periodic functions. And the correct definition of the minimal entire solution is following. The solution psi is analytic in the strip real part of z is less or equal than h. And second, the function a, b, c, and d are bounded as z tends to plus I infinity for a and b, and as z tends to minus I infinity for c and d. That is the definition. One can prove that there is only one solution having this property up to a constant factor. And if you have a solution which increases more quickly at infinity, it's zero. That is the exact definition.
Okay.
Okay.
Any other questions?
The end of the conference.
No, there is one other talk.
Okay.
Okay, anyway, thanks a lot.
Thank you very much. Thank you.